Linear and binary search in Java. So, this presentation will hopefully teach you about the importance and implementation methods of linear search and binary search. These are both methods of achieving the same desired result, which is trying to find the index of a given value. So if our given value is 1 here, the index of it is 0. Linear search is one of these methods. It's a simple algorithm used to search for a particular element in an array, and it works by sequentially checking each element in the array until the target element is found or the end of the array is reached. This can be implemented on unsorted or sorted lists, and it takes minimal setup. An example I like to give is you have a collection of books here, and the way you would apply linear search to these is you'd look for your desired book by searching the first one. If it's not the first one, then you search the next one. If it's not the next one, then you search the one after that, and you keep repeating the process until either one of two things happens. You A, find your book, or B, finish searching through the whole list. Here's an array. Target value is 6. We know our index is 3, but how would we find that using linear search in Java? So we check index 0, check index 1, check index 2, check index 3 until it reaches 6. We would set up our array, set our target value to 6. We'd make an integer right here, I, that keeps track of what index we're searching for at the moment. And while the array at that index, our value is not our target value, continue looking through the list. We're going to make sure that we're looking only in the list's length, and if we reach our target value, we break out of this for loop, we break out of the while loop. Otherwise, once we reach the end of the list, we'll finish with our for loop and break out of the while loop. Now, if we found our value inside the list, we'll print out our target value is at index and then whatever our I value was. Otherwise, so if our array at index I wasn't our target value, which means we finished through the list and we couldn't find it, we'll just print out that our target value is not present in this array. Now, I'm going to compile and run this with our target value being 6. Our target 6 is at index 3. Excellent. Okay, now let's check 13. Our target value 13 is at index 5. Great. Now let's put a value that isn't in this array, 100. Okay, and let's run that. Our value is not present in this array. Good, great. That's exactly what we expected. What does the runtime look like this? So the worst case would be O of n, where n is the size of the array being searched. So the most amount of time it's going to take is big O of n, where n is the length of the array because you went through the whole array. The best case would be O of 1, where it's at the first index, so index 0 of your array. That's where your target value is. You only have to iterate the loop once. And the average case would be O of n, where n is a number between 1 and the size of the array. So, binary search, on the other hand. Binary search is a popular algorithm used to search for a particular element in a sorted array more efficiently than linear. This is more efficient in memory and in time. Mostly. It works by dividing the array into two equal halves and checking whether the element being searched for is in the left half or the right half. This process is repeated until either the element is found or the search range has been reduced to 0. So you're dividing in the same spot again and again. This can only be used in sorted arrays and is more efficient in memory usage and speed than linear search. Now, an example I like to give is you're looking for this moldiest piece of bread. So the way you'd find it is you cut this toast in half, and you see is the left side more moldy or the right side more moldy. If the right side is more moldy, then you cut this remaining right side in half. You keep dividing until you find the moldiest slice of bread. And then we have the same array. Our target value is 6. We're looking for index 3. That's hopefully the result we're going to get. The way we do this is we place a value at the back and at the front, and we'd average the two out to make I. Now, if our array at I, so 8, is greater than our target value, which is 6, then we basically cut off this whole side by shifting C over to I and leaving B the same. So now we're left with this gap. On our second division, what we do is we average these out to find I, and if the array at I, which is 5, is less than our target value, which is 6, then we'd keep C the same, we'd shift B over, and now if we were to do this a third time, our I value would be placed right on top, right here, of index 3, which is our target value is at index 3. And here we can see I set up the array, the target value, our back, front point, and the middle point. We have another loop. This is if our point is greater, it sets C to 1, C to I. If it's less than, it sets B to I. This is all the math that I did before on the other side. That was just explained in simpler terms. And here we have the option where if C is equal to I or if B is equal to I, this would mean that you're dividing on the same spot. So we'd have to stop our program and say that our target value is not present in this array because we're looking between values at that point. Otherwise, we just print our target value is at index I. So let's try this with 6. Let's compile that. Let's run that. Our target value 6 is at index 3. Perfect. Okay, let's try this at value 16. Our target value 16 is at index 6. 0, 1, 2, 3, 4, 5, 6. Perfect. And let's do it for 34,568. All right. Our target value is not present in this array. Perfect. Okay, great. Now, what are our runtimes for this? So the worst case time complexity of a binary search algorithm would be O of log n, where n is the size of the array being searched, and if our specified value is not in the array, our n can only be at most the length of the array. So the best case would be, once again, O of 1, but that would mean that our target value is directly in the center of the array, since I would land on the first division. And the average case would be O of log n, where n is likely to be some number between 1 and the array length. What are the advantages and disadvantages of each method? So, linear search is easier to implement, and it works with any data type, even unordered lists. Some disadvantages of linear search is it can be slower than binary search, because linear search uses a linear function, O of n, whereas binary search uses a logarithmic function, O of log n, which kind of cuts off if you know what a log function looks like. Some advantages of binary search would be fast performance, like I said, and it's efficient for stored data too. So not only is it more efficient in speed, it's more efficient in memory, because if you were to store the values that you divided by, you'd have to store less than if you search the whole list using linear, in most case scenarios. Some disadvantages of binary search in Java, though, are it requires sorted data, so you can't use it on an unsorted list, and it's more complex to implement. Real-life applications of linear search. So you could find a word in a document using a Control F function. It would scan through every single word and see if it's what you were looking for. Or you could look through a product in a grocery store, just running up and down the aisles, checking every single product if it's the one you're looking for. Some ways you would use binary search is in a guessing game where, for example, you have to pick a number between 1 to 10, and I say 5. The other person would say either higher or lower, and so I'd pick 7 if the other person said higher. Right? I'm using binary search to find the answer to that in the most efficient way possible. Now, I've left some homework. You guys have to read the review sheet and finish the worksheet I have attached. Hopefully this presentation has been enjoyable and educational. Answers are provided on a separate document, just a reminder.